So today we will try to finish through all those. Uh, we will deep view learning variants to the creating the training loop, and we will try to finish this off. I think 59 minutes should be enough for this. Yep. If you guys have, I will suggest to play with the to play around with the code because that's what we will look at today. That's the important thing. Theoretically, yep, I think so. We are uh, there yet because we discussed last time the implications of the Q learning and the various improvements that have been done uh, upon it uh, and the differences. Uh, so we will take a look through all of that initially. uh, the various uh, mm, allegations with respect to those improvements that and stabilization that were done to make those from a practitioner's point of view a much uh, how do I say it uh, much stable convergence factor, and then we will go on to the TF agents. We will try to finish the architecture and how a custom TF agent can be formed. What is the pre-processing layers, the con layers, and all, replay buffers, and the corresponding observers. How much is kept in memory and how those trajectories are mapped. And the metrics. And yep, we will try to go as far as time permits. And let's see. Uh, Hi guys. I think so. How was the reading session for each and every one of you guys? Did you manage to run the code and play around a bit?
I'm sorry, Mike, I had to step away. What was your question?
Did you manage to run the code and play around a bit?
Uh, Not I.
Okay, because that's totally dependent. Um, hmm, uh, okay. Uh, so what we can do is get through the basics of uh, TF agents today, and on Sunday we might, with the tutorials that I've shared, everyone will be able to run it on Colab, and uh, we can also go through the documentations, the guides that they have provided, which are specifically for the TF agents, because the theoretical uh, the uh, theoretical how do I say it? The formulations that we have seen does not do not specifically apply to them to the practical purposes, as there are multiple tricks that we have to use to get it to work. As I've shared in the previous uh, you uh, lectures and in the Slack too. But yeah, uh, and therefore we need to look at this from an implementation perspective too. So that's why I was focused on it. Um, no, no worries. I will get.
I
Mhm,
have a comment. That is that the reading assignment that you gave for today is way too ambitious, I believe. I mean, it's 23 pages, and I was only able to get maybe 10 pages into that.
mhm,
And given that you have another 2 sessions after this one to
mhm,
finish, because we planned 6 sessions and this is the fourth. So we don't have to get through all this material tonight, and indeed we won't be able to. I mean,
mhm,
so but I guess I was able to run all the code on my the notebook on my personal machine. I didn't try it on Colab though.
mhm. Okay, cool. Colab is the since the this API has evolved, and I was looking at the functions and there are many more implementational aspects to it than the vanilla. It's the author has shown here the vanilla agent that we have to make to beat breakout game. So I was thinking if someone wants to go into the details, we can run through those TF agent tutorials that are on TensorFlow's site because they are also useful too. If we have time, uh, let me try to finish up the theory part today. We will be dealing with on the next two sessions with the practical aspect of it. So I think that will work out beautifully. So let me now share the screen. Yep. I think so. You guys can share, can see my screen.
Yep.
Uh, so let's start from the deep Q network where we left off last time. Uh, we took a look at this guy here, Q learning, implementation of how the target Q values, in which our state transition pairs are known, uh, and the difference it is to uh, the DQN part, in which the state and actions are not exactly those transitions are uh, not exactly known, and we have to find it out ourselves, those transition probabilities, and hence the convergence here is around 7,000 steps here, if you can see from the graph that we have trained. So uh, that that was the difference that we catered to. This was in a 2013 paper by DeepMind, the fixed Q value targets, in which, yeah, they had specified this with respect to the online model and target model, which is not a hardcore uh, mm, vocabulary, or in the sense a concept, but just from the perspective of this paper, what they have given it. Um, this here in this game, we have used um, the interval of 50 episodes to copy the weight from the online model to the target model, and then perform our uh, calculations. So this was it last time that we discussed. Um, uh, then there was a deep Q network, which estimated. Yeah. So this is the deep Q network here. Uh, Here we took a look at the Q values. The target model will always select which will largest Q value depending upon the max operator, and this will most likely overestimate the true Q value. And what they did here, this was the issue in this DQN algorithm, uh, the double DQN, and this was the issue in the target, the fixed Q value targets, and what they did was to introduce double DQN, and this solved it using the target model. Uh, we discussed this last time too. Uh, they proposed an online model instead of the target model when selecting the best actions for the next states, and using the target model only to estimate the Q values for the best actions. This was it. And this was a change they made. And the graph with respect to the computation, yeah. Uh, I have that very famous. Which can break out. Just incredible. So this, if we take a look at the top left on the aliens graph, the red one is the orange one is the DQN, and the blue one is a double DQN here. So that's the value estimate that we get. And This is between the number of number of training steps, and that's the true estimate. Here, the blue line here, which is shown. Uh, the orange line is the DQN true estimate. That's the convergence, and the how do I say it? The median over the two shaded areas, and how much time will they take to uh, converge. And the median is this guy here with respect to the DQN and a double DQN in which they use. So uh, this was uh, a implementation which of course had much higher compute, but uh, with since in a loop being added here, but yeah, this is much more close to the optimal, and this was one of the breakthroughs of 2015 paper. Then we take state with this. Is there anything I missed? Well, let's take a look through the if they have given here the definition for the tutorials, the discussions. So this was the update. This is the main raison d'etre of this guy here. This is the main equation and how double DQN performs by replacing the targets of those initial values with secondary argmax of the Q with respect to the next state action and parameter theta. Now that's the theta parameter which we have, uh, which we need to take care of in the double DQ and implementation. And this was mostly it. And they here they also uh, experimented with many other elevations and policies with respect to some, I think so, over optimization, uh, the scores across all the games, and how did they tune it, uh, the upper bound, and all that stuff, which is common with classical RL algorithm. But yeah, this was the this is the basic thing, this equation here, which they have implemented in code. Let me see it. Yeah, this is it. This is the training step. This is the mask, the 1 hot, which we took. Then the next best Q values along the axis of 1, since the uh, uh, we have to submit across the axis of 1, since the 0th axis contains, I think so, the uh, the implementation perspective. Yeah, it is simply the number of how do I say it, those transitions. So axis of 1 will have, at each time step you will get that uh, summation across the number of uh, how do I say it, those individual uh, next state uh, uh, predictions. So, and they are summed across, and then those target Q values are calculated from the next best of Q value. So it's kind of a max operation that is being performed here. And then after this, it's being reshaped and the mask has been re-evaluated. And with those uh, target Q values, those gradients are then back propagated here. And those gradients are uh, yeah, calculated and then, sorry, back propagated here. These are the 2 steps that, yeah, we have. Uh, that's the loss here is the mean loss that we have taken. I think so. Loss function was Huber loss. Sorry, that's the Huber loss that we have taken here. On the basis of this uh, algorithm backpropagated its gradients, and the next thing that we take a look at is the replay memory. Replay memory was implemented as a DQ of 2000 length here. And what they did, what is the prioritized experience replay or the replay memory here suggests is a kind of a prioritized, a kind of an important sampling of the prioritized experience replay in which those uh, TD errors, uh, temporal difference errors, are um, which are calculated, which reduces the variance, and it kind of improves your biases towards the uh, experiences that are uh, important, that will get you to the optimal policies in a match that is close to the optimal policies. So that was it. And the formulation here was this. When the each x in to do that, we had to create those experiences. Uh, and how do we create those? We had to have experience training weights as W is equals to uh, N uh, dot P, and as the power of minus beta, where N was a number of experiences in the replay buffer, and here it's 2000. And beta is the hyperparameter that controls how much we want to compensate for the importance sampling bias. So 0 means not at all and 1 means entirely. So this was it. They use beta is equal to 0.4 at the beginning of the trainee, and linearly they have increased it. So if you can see here, this beta factor is being taken here. This goes absolute target. This is the online weights with respect to each step, the soft updates at each step. But yeah, we had to uh, see. Yeah, here it is. It's being scaled according to the initially they have taken zero point 0.4. So I've implemented here in the next. Let's go. So let's say so the ranges. This okay. Let's move forward. I think so. They had implemented it, or I must have looked at a separate implementation. Okay, I will update it in the Slack once I've done with this. So let's move forward here. But yeah, this is simple. And if we look at the paper, prioritize experience replay, there are in the paper they have two implementations. One was the proportional prioritization, and another one was the rank-based prioritization. Both have their own advantages and disadvantages, but they have in the end gone through the proportional prioritization with respect to the gradient clipping and all that stuff. This is the uh, algorithm. Uh, so if it's simple, we just take a look at it. And so we input the mini batch, then initialize the replay memory here. Uh, these are the parameters with respect to the step size, replay period, size, and exponents, alpha and beta. And we from the state is the S node, that's the initial state, and the action we choose for that initial state from that particular uh, policy. Uh, and then we observe and then store the transition at the maximum priority here, where P of t is equals to max of r is less than t. And then from t is equals to 0 to mod of k, where replay period here is k. And if this is there, then this is the inner loop that I was talking about with respect to those prioritized mm, replay that we have taken here. It was 2000. Then we computed this importance sampling weights. Those 3D errors were computed. Then the transitioning priorities and the weight changes were propagated back. So this was all of it. Uh, if you go through this paper, they have tried various different types of prioritization techniques and the implementational. Uh, they have thought about the implementational viewpoint of three or four techniques here. Uh, in the end, they go through the uh, uh, proportional prioritization uh, uh, with because they had, if I could quickly look at it, uh, this paragraph here, the discussion sections of this paper on page number 8. I will update this too. This gives a interesting elevation with respect to those two types of prioritizations, the rank based and the proportional. And why did they go through proportional prioritization? If anybody wants to read uh, or they have a specific area of research that they're trying, then this is it. Okay, now let's move forward to a dueling DQN. Dueling DQN was yet another improvement, and what they did was they employed. I've shared this in the Slack too. Let me take a look at the picture here. Yeah, this is the main thing. We have the state values and the advantage values here. And this is the way of implementing these dueling queue networks. The implementation is quite simple, really. Uh, as I've shared in Slack, but yeah, uh, we have to get a kind of intuition behind why this works. Um, why this works is because of a kind of a guiding principle that you can say. If we talk about in the uh, from a high level or from an intuition perspective, why this works is the state values here, which we have at, if we look at it, this is a smaller uh, vector or a tensor unit with respect to this guy here, the advantage values. So this two are being streamed and uh, 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 this from the 7x7x64 from the feature learning module. And the value stream here represents a kind of a guiding principle for the advantage values to select uh, uh, a kind of uh, uh, a best possible representation of uh, how do I say it? Hmm, uh, best possible representation of an action that is needed to be taken. So, which is according to this formula. The Q will be equals to V plus A minus the A dot mean of this guy here. So this helps in a parameter that helps in the in decreasing the variance with respect to choosing the best value here. So that was why dueling DQN was proposed. And it helped dueling DQN. Yeah. So this was the uh, implementation here, as we have seen. We have taken the raw advantages, those simple formula with respect to the value and the action streams. This guy here, the state value and the add quantity values here. Now let's go on to the rainbow paper. Here in the rainbow implementation, what they did was use six different techniques, and they did was why they did it was uh, to improve upon the previous state of the art results, and they combined all those six to extend this TQN so that the results that we have here, you can see the black line here, the rainbow one. It surpasses everyone, the all the implementations, the DQ and the double DQ and the prioritized, the dueling, AC3, the distributional, and the noisy. So this was the uh, reason why this performed. And I have also given iTouch implementation if you want to do a rainbow uh, for this. Uh, mm, in the code, here we do not have implemented, we haven't implemented, I think so, rainbow, because yeah, we need to combine all that aspects, but mm, uh, this was a rainbow uh, implementation that I found that worked easily here. So you can use this. So now moving to the TF agents library. Any questions up until now? Because this is the basis of uh, uh, the till until Rainbow. This was the basis of all the uh, implementations here. We haven't still looked at the state of the current state of the art, but yeah. Hmm. Okay. Let's move forward to this. Okay. We have used the replay memory here for the deep queue networks here. I wasn't able to get here with respect to those 2000 DQ expressions. Uh, this is a day one step. Okay, they have implemented it from the starting here. Okay, now let's take a look at the TF agents. So this is a library that was developed for the. It's a kind of a uh, 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 library that can be encapsulated by the Open AI Gym 2, and it can uh, uh, support Firebullet, DM control. That's the Deep Minds one, and the Unity agents, Unity's ML agents library. and they have implemented reinforced DQN and DDQN. And I have shared the tutorials link to with respect to these guys. And yep, we can play around and get to the nitty-gritty of that. But let's first take a look at the overview. This is the famous breakout game that we're trying to solve. Uh, then this is the installing the TF agents here. Mm, It's quite new. Uh, this is with respect to those the new improvement of this APIs. Mm. Then we have those TF agent environments here, which we have loaded here from the suit gym. Yeah, yeah. Go to the code. Yep. This is the action repeat environment. Um, oh, sorry, this is the wrapper here. The TF agents has a TF agents wrapper, and this is the action repeat wrapper. And this is the uh, Atari's unwrapped. We have a wrapper that's around the OpenAI gym. Then we have given a list of those wrappers that we have. So as I've alluded to earlier, this contains a wrapper around many of the uh, common functions that we use from a reinforcement learning perspective. This has a description. So this is 1, 2, 13 wrappers that we have. Of course, this has evolved over time, and uh, the we can go through the details of each and every one if the time permits. Then the suit gem.load function with respect to those wrappers here is on. We have used the breakout v4, the partial uh, with respect to those time limits and the maximum episode steps of 10,000. And the environment wrappers is partial, the action repeat, and the times is 4. Here, this corresponds to the I think so. This was mm, I do not know what this partial holds. Let me check this out. This is a generate with respect to okay. Arguments of the key equals. Okay. With respect to those environment wrappers. Okay. So I think so. This will combine it in some fact in some fashion. Uh, it's a function tool with respect to those functions. Okay. Those gym wrappers that is max episode steps. Those action repeat with the times of 4. Here we have used the time 4 so as to get to know the location of the uh, moving uh, this guy here, the uh, uh, if we can say the ball that is about to hit the brick, because we need to have those four a minimum of four time step of objects in the four frames of uh, particular game in how do I say it, in our memory to get a view of the velocity and the direction, the speed and the direction that computes the velocity of a particular uh, movement of this uh, ball, if we can say. Mm, then it's this was the basic formulation at uh, as we have seen earlier with the whole environment. Um, what are the step types, the rewards, the discount, and the observations that did return if we use it once. This was the environment specifications of what this wrapper returns, the observation underscore spec, the action spec, and the times step spec. Then these can be initialized as a specification class, nested list, or dictionaries, and these are the uh, key action pairs. Sorry, the dict, uh, those nested structures that we have. Then they have done here is they have just nest. Okay, but it is not such a nested data structure. Okay, yeah, nest is a for the nested data structures tool here. I think so. They have used it to develop those frame stack of four agent Raffles solutions. Yep. Then this is with respect to playing a few steps just to see what happens. About observations, the figure sizes with respect to this guy here. This is the just creating a Python environment to TensorFlow environment. That is simply the plotting of observations here. So this is with respect to the environment specifications that we have just looked at. Of course, there are many other Atari preprocessing and Atari wrapper sub packages to explore, and they have I don't know tens of classes here with respect to those frame stack and different implementations of the various techniques that we use to solve this problem. But hmm, this is a particular example of it. I think so. This is clear. Or do you guys have any questions here? Okay. Now let's go on to the environment wrappers. This is the package that we were looking at. TF agents in environments.wrappers. And the take took take I think so. Yeah, we in the examples here we took a look at action clippers, action discretize wrapper, in which this will uh, uh, change the continuous action spaces into discrete steps, and with respect to the number of bends that you need to have. Then the action repeat, we have taken action repeat 4 here. For, sorry, we have taken frame stack as 4 and action, I think so, while accumulating the repeat of the rewards. So we will use it down the line. And then the run stats, the number of steps and the number of episodes, and then the time limit. Uh, and if the interrupts the environment for longer than the maximum number of steps that it has to run. So sometimes it may go uh, in a particular episode. If that final state is not reached, then the agent may try to roam in the environment, and yeah, that then we have action repeat, simple implementation of action repeat here with respect to that environment and times. Then we simply load the breakout v4 game. So we have a lambda environment with respect to the time limit and the action repeat here. What we did was look at partial. Yeah, that's why I was a bit confused. They have used partial here instead of lambda. And up to to do the same here. So it's just a kind of a different implementation, but they are doing the same. Then they provide a handy Atari preprocessing wrapper that implements them with respect to the grayscale and downsampling, max pooling, the frame skipping, and the end on life lost. Uh, so these 4 are the pre-processing steps. So okay, let's go through each one of them one by one. Grayscale converts the uh, observations into grayscale and downsample it by default to 84 cross 84. Then the max pooling filter is being applied, which compresses it across the spatial uh, uh, domain, uh, which uh, of course, this is to remove the flickering that occurs in some games with a limited amount of sprites that the Atari 2600 could display in each frame. Okay. Then the frame skipping is done with respect to every end frames of the game is inputted here. And this speeds up the game and training because of the rewards are less delayed. So it uh, uh, effectively batches those. And then in the end of life lost, the agent gets no immediate penalty for losing a life. Uh, uh, this may be helpful in Montezuma's Revenge, in which you have to have those kind of a bomb DPs, the partially observable states, in which you can sample those based on the not on the last the last step that it has taken, but with respect to the other properties too, the rewards that it has accumulated over that lifetime. So, uh, uh, so that was the pre-processing steps with respect to that Atari wrapper that we talked about. And since Atari pre-processing already applies random frame skipping and max pooling, we need to use a variant of breakout no frame skip 4 version 4 here. Uh, that's a non-skipping variant that we have from the frame skipping perspective. And as I have alluded to, from a single frame, it's insufficient to know the direction and the speed of the ball, and which is sufficient to play the game. One way to handle is use the environment wrapper, which will output the observations of the multiple frames stacked on top of each other along the channel dimension. Then the max pool is being applied here. So it compresses it across those channel dimensions. Yeah, a bit confused with respect to those dimensionalities. Yeah, yeah. And then this is the 2700. Why we have taken here 2700? Because it will be multiplied by 4 for the frames. So if we effectively take a look, it will be 108K frames. This will be it. Chip environment wrappers for the Atari processing, and then the frame stack is being applied. So that will be the list of the environment wrappers. Mm, yeah. So if we take a look at it programmatically, these frames are stacked across the channel dimensions. The red represents the frame from the 3 steps ago, green represents 2 steps ago, and a blue is the previous frame, and the purple is the current frame. So this is the practical view of how those frames are pre-processed. We can interpret it according to this. So if you can see this, this is the movement, the direction of the ball, the speed and the direction. So here, this is the direction that the ball is heading, and we can calculate the velocity too, the speed too, based on how fast it is moving. Then this is the wrap. This is the wrapping of those uh, environment that we just created to a TensorFlow PY environment. This will make it uh, work across the TensorFlow graph. And it will easily work on the GPU. And yeah, um, this will support both the Python and the TensorFlow based environments. We have looked at this function before, the tf.py function, which allows the graph to call the arbitrary Python code in the particular uh, context or a gradient function that we had. So we can convert any function to use this uh, uh, to be called from a TensorFlow graph. So that's the advantage that we have. Instead of subclassing a particular TensorFlow class and then try to use those overridden methods, yeah, we can do it this way too. This is a nice breakout environment, and we have applied the pre-processing and the TensorFlow support, and we create a DQ agent, and we will look at the training architecture next time. I think so. I am over time right now. Yeah. Just to add, in this pre-processing steps, we can have some sort of auto argumentation to being applied to it. Suppose this is the direction of the ball that is heading, and we can use this to argument our environment uh, uh, to have some sort of uh, mm, those uh, uh, how do I say it? Those changing of those environments, those pre-processing stacks of code that can be mapped across and argumented with some sort of uh, 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 how do I say it? Those noise and those simple bilinear or transformation or screwing or squeezing, or yeah, there are, I think so, the basics are there are tens of graphical argumentation techniques, and recent research has showed that those argumentations that are being applied improves those um, uh, Python, those training in the Atari and many of the state-of-the-art environments that folks are using to train it. So there are multiple research papers that you can find with a simple Google search, which improves upon that too. So this was with respect to the pre-processing steps that we could do. Uh, the next time we will take a look at the training architecture and the other stuff, and we will try to finish it. Because this is since we have already gone through the theoretical aspects, this is the mechanistic part, and we have already gone through the basics of TensorFlow and the implementations, and it's just uh, the things that we are already kind of familiar with. We just have to add it to this kind of framework. experiences from the last, what do I say, from the last sessions that we have. Yeah, this is easy from now on. Just with that, any questions?
Okay, so where will we start next session? What section will we start on?
So we will start with the this guy here, the training architecture.
Okay.
Yeah, the training
Okay.
architecture, and we will take it from here and try to finish as much as possible. Because and please run the code once and go through the steps too before we jump on the call.
Okay, that's great. I think we got through a reasonable chunk of material. That's 10 pages. It's pretty dense because, you know, a lot of this stuff he just talks through, and it's hard to. It seems very abstract when you read through it.
Mm-hmm.
It could, the material could be a course in itself, and there are whole books, and really good books. In fact, I think it was Brandon Rohr and a few other people who've been tweeting about the reinforcement learning book that's out.
Which one is that?
I
Is it a new one, or is it the same one? Is it the Sutton and Bartow one?
think it's the same one. Bear with me, please.
Sure.
Yeah, I would like to say a couple of things in this too. Since we already know there have been so many research papers already being published, and those techniques that are already there. Yeah, I think so. This book represents the techniques up until 2018. The rest of 2019, 2020, they that's a couple of years of recent advancements that we have missed. But yeah, we can take it from here and come to the state of the art, and then try to in the next couple of uh, um, sessions, I will try to capture first get to this, and then try to capture the recent state of the arts that are being there, that are being presented right now in the conferences all across. Matt, you were talking about the book.
Yeah, I was looking it up. I think I saw him posted on LinkedIn, not Twitter. My apologies. Is one of the lawnmowers going back?
Also, if you want to take a look at an alternate OpenAI, uh, OpenAI's practical resource of implementing those key algorithms, we'll just share it in the chat here. It's necessary to. we try to build up around this. It's also a great resource for giving a introduction to spinning up a deep RL agent in as much few lines as possible without much headache. And and we also have those concepts that are explained with respect to we, those key papers, those uh, basic concepts that we need to take into account, or if we have to move in the world of RL. So this is
Well, okay, the book is Mastering Reinforcement Learning with Python by Inez Bilgin. His last name is spelled Bilgin. He works for Microsoft's Autonomous Systems Division. He got his degrees at Boston U, and he's also taught at UT Austin. This particular book goes into, by the time you get halfway through the book, you get into the content that we covered today with DQNs and so on.
Wow, this thing is only $5 on Kindle. I just posted it on Amazon.
Okay.
in scaling possibilities, yeah. It's a good book from the looks of it.
Yeah, and let me just take a look at Amazon.
Yeah, even include meta learning.
Yeah, $5 on Kindle. How is that?
Pretty amazing.
Management, implementation in the personalization and marketing and finance too.
Yeah.
This is more from a practitioner's point of view.
Which is ideal. I'm speaking for myself.
But the book that Sutton and Batuan we are going to go through, that's from a theoretical point of view. But of course, we can argument it, which I think I will be doing with the algorithms and try to see it from the practitioner's point of view, as Jerome has done here. No, but also, I'm currently into a bit of research. So, uh, from my perspective, that theory works out to be a better. How do I say it? Kind of. It's my raison d'etre. Theory is.
so you're really excited about it. That's currently, is that it? That's very nice. Yeah, I hope we can make the course a combination of theory and practical stuff, because I think it's a shame to just learn the theory and not really learn how to do anything with it.
Yeah. Because that's where the most of the things happen. Because in theory, yeah, we can have those upper bounds and lower bounds with respect to particular assumption of a or a particular bounded problem that we are trying to solve. That works in the research pure settings, but when you try to implement that, only those sub part of, or only those concentrated parts have to be uh, uh, looked at or implemented, and that too in a uh, kind of a toy environment or those data sets that we use. But if we look at, yeah, so from the from the real world perspective, both of the theoretical and practical implementations are necessary. Yeah, totally
Yeah.
agree.
Sounds good. Okay, gentlemen, shall we call it a night?
Yes, please.
And we'll see you all on Sunday with Mayank's 5th installment. And yeah, this is the longest chapter. It really is, and
Yep.
but we're doing well, I think, getting through it.
Yep. And Maya, good morning, and thank you for everything.
Yeah, thank you,
Oh.
Mayank. Very nice.
Thanks. Thanks, guys. Take care and please try to run the code before coming in.
Okay.
Thank you, Mayank.
Okay. Good night.
Okay, bye.
Right.